Hello and welcome to my YouTube channel. My name is Yasser Khan, and in this video I will be going through logic gates. Before we get started, it's important to know that for your exam you're expected to understand and define the functions of logic gates and be able to draw truth tables from given circuits and vice versa. So before we get started, it's important to know what a logic gate is. Logic gates are basically building blocks of any digital system. It is a circuit having one or more inputs and only one output. The combination of these gates create logic circuits that will allow a specific function to be carried out. There are 6 gates that you need to know about for your exam. These are NOT, AND, OR, NAND, NOR, and the XOR gate. For your exam, you should be able to label each one of these gates, draw them, produce a truth table for each of the gates, and also explain how they work. Let's start off with the NOT gate. The NOT gate is considered as the most simplest gate out of all 6. Another name for the NOT gate is the inverter gate. It only accepts a single input compared to the others and produces one output like all of the others. So if you put 1 in, you'll get 0 in return, and if you put 0 in, you'll get 1 in return. Below is the truth table for the NOT gate. Consider A as the input and Y as the output. If we input 1, the output will be 0. If we input 0, the output will be 1. The AND gate takes 2 inputs and produces 1 output. For the AND gate to be true or 1, in this instance, both of the inputs need to be 1. If input A is 1 and input B is 0, then the output will be 0. If input A is 0 and input B is 1, then the output will be 0. And if input A and B are 0, then the output will be 0. The truth table for the AND gate will look like this. Input A, B, if they're 1, the output will be 1. If input A is 1, B is 0, the output will be 0. If input A is 0, input B is 1, then the output will be 0. If both of the inputs are 0, then the output will be 0. As you can see from this truth table, both of the inputs for the AND gate need to be 1 in order for the output to be 1. It's important that you understand this and know this for your exam, as it is bound to come up. The OR gate has 2 inputs like the AND gate and produces a single output, however it works differently. If A and B are 1, the output will be 1 in the OR gate, like the AND gate. If A is 1 and B is 0, the output will be 1. If A is 0 and B is 1, the output will be 1. And if A and B are 0, then the output will be 0. The truth table for the OR gate will look like this. A and B are all the different combinations of inputs, and Y is showing the output. As you can see from the table, the only time the output is 0 is when input A and B are 0. XOR gate, also known as exclusive OR gate. This gate takes 2 inputs and produces a single output. If input A and B are 1, then the output is 0. If input A is 1 and input B is 0, then the output is 1. If input A is 0 and input B is 1, then the output is 1. If input A and B are 0, then the output is 0. The truth table for the XOR gate will look like this. As you can see, the output is only 1 when either of the inputs are 1. If both inputs are 1, then the output is 0, and if both inputs are 0, the output is 0. So either A or B have to be 1 in order for the output to be 1. The NAND gate. The NAND gate is a combination of the AND and NOT gate, so the output is the opposite of an AND gate. The NAND gate takes 2 inputs and produces a single output. If input A and B were 1, then the output would be 0. If input A was 1 and B was 0, then the output will be 1. If input A was 0 and input B was 1, then the output will be 1. If input A and B are 0, the output will be 1. The truth table for the NAND gate will look like this. As you can see, it's only 0 when both of the inputs A and B are 1. So it's the opposite of the AND gate. The NOR gate is a combination of the OR and NOT gate, so the output is the opposite of an OR gate. Again, the NOR gate takes two inputs and produces a single output. If input A and B are 1, the output will be 0. If input A is 1 and input B is 0, the output will be 0. If input A is 0 and input B is 1, then the output will be 0. If input A and B are 0, then the output will be 1. The truth table for the NOR gate will look like this. The output will only be true when both of the inputs are 0, meaning false. As I mentioned earlier, this gate is the opposite of the OR gate. Now it's time to take our understanding of logic gates further. Here we have an AND gate and a NOT gate, and we need to create a truth table for this circuit. To start off with, ensure that your logic circuit is labelled with the inputs and outputs, so we have two inputs and two outputs. The next step is to create our table with appropriate headings. So the two inputs we have are A and B. The shorthand expression for the AND gate is Y equals A and B, and for the whole circuit is Z equals not A and B. The next step is to put in all the input combinations. So 1, 1, 0, 0, 1, 0, 1, 0. Now we need to calculate the output from the AND gate. And if you remember from earlier, both of the inputs need to be 1 for the output to be 1. If either of the inputs are 0, or both of the inputs are 0, then the output is 0. So as you can see here, both of the inputs are 1, so the output should be 1. And here B input is a 0, so the output is a 0. Here we have the A input as a 0, so the output is a 0. And the final one is a 0 again because both of the outputs are zeros. The final step to this truth table is the NOT gate. So Z equals not A and B. If we remember how the NOT gate functions, then this should be easy. Whatever goes into the NOT gate, the opposite comes out. So we're going to put in a 1, and in return we should get a 0. If we put in a 0, we should get a 1. 1 again, and finally one more 1. Now we can change the column heading of the final column to Z equals not Y. Let's try creating another truth table for a different type of logic circuit. In this logic circuit we have an AND gate and an OR gate. So we have three inputs, A, B, C, and we have two outputs, Y and Z. So to start off with, we need to put in all the possible input combinations. So we'll start off with 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Now we need to work out the output for the AND gate, so Y equals A and B. As you remember previously when we looked into the AND gate, the output is only true when both of the inputs are true. So to start off with, A and B are true, so the output will be true. A and B again are true, so the output will be true. If either A or B or both are false or 0, then the output will be 0. The final column is based on the input from C and Y. So we will be focusing on these two columns. And as you can see from the logic gate, it's an OR gate. So either one of them need to be true in order for the output to be true. If they both are true, then the output is true. And if both of them are false, then the output will be false. So The first one's nice and easy, both of them are 1s, so the output should be 1. C is 0, Y is 1, the output will be 1. 1, 0, the output will be 1. Here they both are 0, so the output will be 0. C is 1, Y is 0, so 1. Both of them here are zeros, so the output will be 0. Again, C is 1, Y is 0, so the output will be 1. And finally, again, we've got a 0 for C and a 0 for Y. This will result in the output being a 0. There is a very high chance of a question like this coming up in your exam. Drawing a logic circuit for a logic statement. So the logic statement we've been given here is Z equals NOT A and B. And what we need to do is combine the logic gates together to make this statement. As you can see from this statement, we have two logic gates. We have the AND gate and the NOT gate. And always remember, when dealing with logic statements, do the brackets first. So let's break this down. Start with the AND gate as it is in the brackets. Ensure that you add the inputs. Then draw the NOT gate and add the output. So let's give it a go. We've got our AND gate. We've got our inputs A and B. And then we put in the NOT gate and the output. The statement for this logic circuit is Z equals NOT A and B. There is a very high chance of something like this coming up in your exam, where they give you a problem and expect you to break it down to create a logic circuit and a truth table. This statement is referring to an alarm system. A system uses 3 switches A, B and C. A combination of switches determine whether an alarm X sounds. If switch A or switch B are in the on position, and if switch C is in the off position, then a signal to sound an alarm X is produced. So just reading this statement, you can see that there's 3 inputs, which are A, B and C. If switch A or switch B are in the on position, from this statement we can see that there's an OR gate involved. And then it's saying that, and if switch C is in the off position, then a signal to the sound an alarm X is produced. So we can see that switch C is a NOT gate, and joining them together is an AND gate, which will be the output. So let's break it down here. If A equals 1 or B equals 1 and C equals not 1, then X equals 1. The first part is 2 inputs, A and B, joined by an OR gate. The output from the first part and the third part are joined by an AND gate. And the third part is 1 input, which is C, which is put through a NOT gate. So we need to start off with the OR gate and put in the inputs A or B. The next part will be inserting the NOT gate with the input C. And the final part is inserting the AND gate with the output X. Now it's time to check if our logic circuit works as it should. It's stated in the statement, if switch A or B are in the on position and if switch C is in the off position, then a signal to sound an alarm X is produced. So let's put switch A and B in the on position. And let's put switch C in the off position. So the output from the OR gate would be 1. The output from the NOT gate would be 1 also, as it's the opposite of what goes in. In order for the AND gate to be 1, both of its inputs need to be 1. There you have it, the first part has been successfully completed. Now moving on to the second part, we have to produce a truth table for this logic circuit. So to start off with, we need all the possible input combinations. So we can have 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. These are all the possible input combinations that we can have. Now we need to work out the value for output X. What we know so far is that the OR gate, either one of the values or both need to be 1 for the output to be 1. For the NOT gate, the the value needs to be 0 in order for the output to be 1. If the value for the NOT gate is 1, then the output will be 0. In order for output X, both of the inputs need to be 1 because it is an AND gate. If either of the values are a 0, then output X will be a 0. So let's have a look at the first output. So if we have 1, 1, 1, the output will be 0 because the input into the NOT gate will turn into 0. The second one would be a 1. The third one will be a 0. The fourth one will be a 1. The fifth one will be a 0. The sixth one will be a 1. And the final two will be zeros because A and B are zeros. It's time to have a go at some exam questions and to check what you've learnt so far. The answer to these questions will be in my next video. Draw the logic circuit diagrams for the following expressions. Z equals not A or not B. Z equals A and B or A and C. A system controls the flow of vehicles through a barrier based on 3 lights, A, B and C. When a light is red, the signal is 0. When a light is green, the signal is 1. The barrier will open when the output is 1. The barrier opens if either light A is red and light B and C are both green, or light A is green and light B and C are both red. Design a logic circuit for the system. Create and complete the truth table for the system above. 3 switches, A, B and C each send values of 0 or 1 to a logic circuit. Value X is output from the logic circuit. Output X has a value of 1 depending on the following conditions. Switch A sends value 1 and switch B sends value 0, or switch B sends value 1 and switch C sends value 0. Draw a logic circuit to represent the conditions above. Complete the truth table for the conditions given above.